Hello, everyone. My name is Saniya Heeba, and I'm a postdoctoral researcher at McGill. And today I'm going to be talking about some of the work that I did when I was a PhD student at RWTH Aachen, titled Freezing in a Hot Bath. So let's get started. The premise of most of my work is that we don't really know what 80% of the universe is made out of, which is to say that if we think of the universe's matter budget, all of the things that we can see or touch, such as fluffy cats, or stars in distant galaxies, or pancakes with too much maple syrup, only make about 20% of the universe's matter content. As for the remaining 80%, we have very little idea of what it is. We can infer, for instance, from measuring the rotational velocities of stars of galaxies that most of the galactic mass has to be invisible. We also know from studying collision of big galactic clusters that this invisible mass interacts weakly not only with the things that we can see, but also with itself. And of course, we have the CMB, which tells us that the present-day structure of our universe was seeded by clumps of this invisible stuff, which we call dark matter. Since we know so little about dark matter, we can start by asking, how do we make dark matter in the first place? As with a lot of things, we can always look toward the standard model for inspiration. We know that all of the visible particles in the early universe formed a kind of primordial soup or a heat bath, where interactions between particles kept everything in equilibrium. If you think about dark matter as a particle, then it is perfectly valid to assume that it was also part of this heat bath. This is the premise of the so-called weakly interacting massive particle paradigm, or the WIMP paradigm. In the WIMP paradigm, the abundance of dark matter is set by its annihilation into standard model particles, such that starting from an equilibrium dark matter distribution, the dark matter number density decreases with time. Since the rate of these reactions compete with the expansion of the universe, at some point they become inefficient and the dark matter density freezes out. The beauty of the WIMP paradigm is that if we assume weak scale masses and couplings for dark matter, we coincidentally reproduce the dark matter abundance inferred from the CMB. And of course, this is a really cool thing that pops out of the WIMP paradigm. But there is one small problem. We've been searching for WIMPs for several years, and so far none of our experiments have turned up anything interesting. As a representative example, consider this plot from a paper by Rebecca Lean and others, which shows the bounds in the WIMP annihilation cross-section as a function of its mass. Remember that this is the same cross-section that sets the WIMP abundance in the early universe, and the dashed line tells us the exact value of this cross-section. Taken as a whole, although viable parameter space exists for WIMPs, which is the orange line, the fact that it is quite small is a good enough motivation to rethink some of our assumptions in the dark matter story. One of our key assumptions for the WIMP paradigm was that of equilibrium between the dark and the visible sectors. So while we're rethinking assumptions, let's start with that one. Technically, there's no a priori reason for this to be the case, so let's assume that the two sectors have always been out of equilibrium. On top of that, we're going to make another simplifying assumption and also say that we started off in a universe with no dark matter at all. Of course, the question now is, how do we make dark matter, as always? And this time we're going to flip the WIMP idea on its head. We're going to say that dark matter was produced by the annihilation or decays of standard model particles into dark matter. So if we look at how the number density of dark matter varies with time once again, we see now that we start off with a small abundance of dark matter, we populate the dark sector through these annihilations or decays, and at some point these processes also lose out to the expansion of the universe and freeze in. Contrary to the WIMP idea, now the final dark matter abundance is actually proportional to the coupling between the two sectors. So if we increase the coupling, we increase the efficiency of these reactions, and therefore we increase the final abundance of dark matter. But of course, these couplings cannot be arbitrarily large. Remember, we need dark matter to not be in equilibrium with the standard model heat bath. We can estimate the magnitude of these couplings by comparing the interaction rate of the process that drives equilibrium with the expansion rate of the universe, noting that this has always to be smaller so as to satisfy the condition of non-equilibrium. To anchor ourselves at a specific point in time, we can compare these two rates at the electroweak phase transition. Knowing how these two rates scale with temperature, then it is super easy to derive an upper bound on this coupling, although keep in mind that the exact value of this bound will depend on the specifics of the dark matter model under consideration. Now, compared to the wimpy couplings, which are of order 1, this is indeed very small. And just to emphasize on that fact, and since physicists are really good at naming things, we call such dark matter particles as feebly interacting massive particles, or FIMPs, and the production mechanism is called freeze-in. So far, we've only discussed the qualitative aspects of freeze-in production, but in actuality, when we want to compute the dark matter relic density through freeze-in or even through freeze-out, what we do is to solve a Boltzmann equation. This is a simple one-dimensional differential equation that relates the rate of change of the dark matter number density and chi, which we can reframe in terms of a scale-invariant quantity y chi. And on the right, we have the collision term, which basically tells us the rate of the processes that produce dark matter and the rate of the processes that deplete dark matter. Now for freeze-in, we know that the initial density of dark matter particles is close to being negligible, and so the back reaction term can be essentially ignored. And you can reduce the Boltzmann equation down into a simple form where the rate of production of dark matter is proportional to the cross-section of the production process multiplied by the number density of the Standard Model particles that are present in the heat bath. Although this equation looks very simple, in practice, these equations are notoriously difficult to solve. And on top of that, for freeze-in, there are some additional complications that arise and that we need to account for. In particular, if we look at how the dark matter number density evolves as a function of temperature, we now see that for freeze-in, we're quite sensitive to a range of temperatures. And what this means is that we are sensitive to the properties of the Standard Model plasma across various temperatures. Basically, what we need to do is then to account for a number of things. So we need to account for the fact that at very large temperatures, the particles are actually relativistic, and our usual descriptions of particles in terms of Maxwell-Boltzmann distributions are no longer valid. So we need to consider the spin statistics of relativistic quantum gases, and this actually implies a frame dependence in the way that we define our cross-section. So the early universe picks out a special frame. It's not Lorentz invariant. The second thing is that the particle properties themselves are modified in medium, which means that particle widths and the masses in medium are different from their tree-level vacuum values. And finally, since we are sensitive to the properties of the plasma over a range of temperatures, we're actually sensitive to the change in the degrees of freedom that happen as a function of, for example, the different phase transitions that we know of. So for the big picture stuff, what we need to do to calculate accurately the dark matter density is to actually reformulate the FIMP-Boltzmann equation to consistently account for these effects. And once we have that, what we can do is we can apply this to a simple model and actually study whether these effects actually have a relevance, right? So how relevant are these effects? So to start with the first thing, we're going to look at the generic collision term for freeze-in, which looks like a very ugly equation, but it's actually quite simple to understand. So we have a symmetry factor, which basically tells us whether the particles in the initial state are identical or not. We have various Lorentz invariant phase space factors that basically mean that we're integrating over the momenta of particles both in the initial and the final state. We have a delta function that essentially sets the energy momentum conservation, and we have the matrix element that tells us what the production process looks like. So psi here is a Standard Model state. And then we have these phase space factors that give us the distribution of the Standard Model particles in the plasma. So now what we're going to do is we're going to reframe this in terms of dark matter annihilation instead of dark matter production. And the importance of this step will be clear as we go on through the talk. So this is quite simple to do. So we know that the matrix element is CP invariant, which means that the matrix element of production is equal to the matrix element of annihilation. And we can actually change the phase space functions from the Standard Model phase space functions to some fiducial dark matter phase space functions by using energy and momentum conservation. And this is a simple mathematical trick that you can employ. So essentially what we're doing is we're replacing the dependence on the initial states, that is the Standard Model states, to some fiducial dark matter states. Now, this is not the true dark matter distribution, but something that we have made to be Maxwell-Boltzmann by construction. So what this means is that the Boltzmann equation for freeze-in now reduces down to something that looks quite similar to the Boltzmann equation for freeze-out. So we have the cross-section in terms of a dark matter annihilation cross-section. And now this, the important point of distinction here is that this is the complete in-medium cross-section with the proper relativistic spin statistics factors. And then it's multiplied by the dark matter number density, which is not, once again, not the true dark matter number density, but simply a Maxwell-Boltzmann fiducial distribution that arises because of this mathematical trick that we employed. And if you want to know what the formula looks like, it's essentially this equation here. You can find more details in our paper that you can look at in the bottom right of the screen. So what this means is that we now have solved one major problem that we have. We have essentially reframed our Boltzmann equation to account for the explicit frame dependence that we have in the early universe. So now the next thing that we want to do is to actually apply this to a model. And we're going to apply this to the simplest model that we can think of. And simple is a controversial term, but like the simplest renormalizable interaction that you can think of is to add another scalar singlet to your model and make it talk to the Higgs, right? So this is the easiest interaction that you can write down. And the only new coupling that you're adding is lambda HS. So whatever we're doing, the only thing that we're sensitive to is the mass of this new scalar, and the coupling's only two new parameters. And this is essentially like a Higgs portal model, right? So when you think about the Higgs, the first thing that comes into our mind is one of the things that's interesting about the Higgs is the electroweak phase transition. And what this means is that essentially in the early universe, the Higgs potential went from being symmetric to being kind of this Mexican hat shape. And this basically gave all the particles their masses and et cetera, et cetera. It's the usual story. But the important point is that the Higgs mass and web itself that we're used to considering as constant quantities are actually not constant, but a function of temperature. And this is what is shown in the plots on the bottom of the screen. So the Higgs wave starts from having a 0 value, which is when the potential is symmetric, to slowly rising to its constant value that we're used to, which is 246 GeV. And the same is true for the Higgs mass. Now, instead of being 0 for very large temperatures, it actually has some thermal component to its mass, which is basically because of the fact that it's interacting with other particles in the plasma. Another thing that happens through this phase transition is the fact that the coupling structure of whatever Lagrangian we write down actually changes before and after the phase transition. So if you think about this scalar singlet, for instance, we would see that before the phase transition, the only way that we could produce these scalars is through this 4 vertex of the Higgses going to scalars. But after the phase transition, because the Higgs essentially couples to various fermions and bosons, we also have these additional processes where fermions can annihilate into scalars. So we're increasing the number of ways that we can produce the scalar. And this is where the fact that we can write everything down in terms of dark matter annihilation and not production, this is where it becomes important. Because if you write this down in terms of scalar annihilation, what we see is that the cross-section has a very simple form. In particular, we can essentially add all of the Sun model production channels in terms of the off-shell Higgs decay with gamma H. And this quantity is actually very well known and very well computed, which also means that we can generically include NLO corrections to this quantity. And there are some subtleties to this calculation, but I will not go into details. But the fact is that we can make our prediction for the dark matter density more precise just by a simple reframing. Now, this was for the electroweak phase transition, but we have a second phase transition in the Stan model, which is the QCD phase transition. And this essentially means that at a certain temperature, we go from a universe where we have free quarks and gluons to a universe where you have pions and kaons and like essentially bound states. Again, because we are reframing everything now in terms of this off-shell Higgs decay width, we can essentially write down the production channels in terms of these final states. So there would be a change in the degrees of freedom in the Sun model states, and this would change the cross sections. And this is what is shown on the screen. So it's a cross section as a function of inverse temperature. And the solid lines are essentially when we account for the QCD phase transition. So we have fewer final states after the QCD phase transition, which suppresses the cross section as compared to the kind of vanilla cross sections where we had no QCD phase transition. And so this kind of changes once again, because this changes the production cross section, this would change our prediction for the relic density. So to catch our breath for a moment, until now, so what we've done is we've written down Friesen in terms of dark matter annihilation cross sections, and we have included in medium and thermal effects. And we've basically shown how this can be done in a mathematical way, and we've shown how important this can be. We've also included NLO corrections generically, and this kind of pops out from the fact of this reframing. And we've also consistently accounted for the relevant degrees of freedom, again, by simply implementing the fact that we have these phase transitions in the first place. So now we're going to look at what the effects of these calculations are on the final dark matter relic density. To start with, we're going to consider what I call IR Friesen, which basically just means that we're considering that the reheating temperature is much larger than the electroweak phase transition temperature, and it's not a relevant scale in the problem. So we're going to employ all of these things that we've learned so far and see how the final yield of dark matter actually changes. We're going to start with the cross section. And just to remind everyone, what our final goal is to solve the equation which is shown on the top right of the screen, which is the Friesen-Boltzmann equation. Now, the completely vanilla treatment would give us an annihilation cross section that varies with inverse temperature, as is shown on the figure. So we have this bump here, which corresponds to the Higgs resonance, which means just that the process would be quite efficient at temperatures close to the Higgs mass. Now, what we're going to do is we're going to turn on the thermal effects. And what this means is that we would kind of suppress the cross-section at large temperatures. And this is directly related to the fact that the Higgs would have a thermal mass that is different from its tree level mass. Now we're going to turn on quantum statistics, and that kind of enhances the cross-section at large temperatures, which is because of the fact that we have bosons in the initial and final state. Remember that the only process that produces dark matter in this regime is this 4 vertex with the Higgs. Now, for large temperatures, so on the right side of this plot, we see that it doesn't really make a difference, even though now mostly we have fermions in the final state. What this essentially is due to is the fact that we have a boson as a mediator, but we have a fermion in the final state. And those two effects kind of cancel each other out. And we get a cross-section that is more or less the same, even if you turn on quantum statistics. Now, this is done for small dark matter mass of 10 GeV and the coupling that would reproduce the dark matter abundance. But we can do the same process for kind of heavier dark matter where we don't produce this by Higgs decays. And this is what this would look like. So the purple line in this plot is for a dark matter mass of 300 GeV. And it essentially tells us that for large temperatures, we actually get a significant difference between the vanilla treatment and the proper treatment. But for small temperatures, it doesn't really change anything. If we now add on one level of complexity, instead of looking at the cross-section, we look at the yield. So this would be essentially the rate of change of the dark matter density as a function of temperature, or inverse temperature as is shown on the plot. And then it's basically the same plot as before, but this time now we explicitly see the Boltzmann suppression on the right side of the plot, which is because of this NSMB on the top right corner of the screen, which is this Maxwell-Boltzmann fiducial distribution that we added on to our equation. So now we know what the yield looks like, we know what the cross-section looks like. What do we expect for the abundance? In particular, how do we expect the abundance to change? Now, for small dark matter masses where most of the production is via Higgs decays, we would expect very small temperature effects, right? Because most of this is happening at late times. And we also know that in medium effects compete. So kind of like the whole thing would give us something that's not super different for small masses. For large masses, the production is actually close to the temperature of the electroweak phase transition or at larger temperatures. And this means that all of the effects that we've discussed are actually more sizable. And this is exactly what we see when we plot the coupling that gives us the right relic abundance as a function of the dark matter mass. This is on this plot. So for small masses, all of the lines completely coincide, or well, coincide to like 5% or something, which just means that the difference in the final relic density is quite small. But as you go to larger and larger masses, we see that the difference actually increases. And at its largest point, it's about 30%, which is quite a big difference in these density calculations. Now, there are other interesting things in this project, but I'm just going to skip over these slides. I'm going to put them in the Dropbox or wherever we're sharing slides, and we can talk about them during discussions. But the idea is that you can essentially do a similar study looking at models where the reheating temperature is a relevant scale in the problem. And essentially what you're doing is you're shifting the largest available temperature to quite small values, which means that you're sensitive to physics around those temperature scales. And this has quite interesting effects. I'm not going to talk about them, but then the idea is that you basically change the coupling values by quite a bit around these scales. Now, all of this is kind of implemented in DarkSOSI. So if you want to just go and play around with it, you can do that. So it's available on the link on the screen. Once again, this will be shared, so you can just click on it. And yeah, so final takeaways from this talk would just be that in medium and thermal effects may be relevant. They're not always relevant, but they may be relevant while calculating phase and abundance. And you need to make sure that you're taking them into account depending on the exact model and the exact temperature ranges that you're interested in. And most importantly, these can be incorporated in a general reformulation of the Boltzmann equation. So because we have very precise calculations of the dark matter annihilation cross-section, because we've been studying WIMPs forever, you can actually just use them for FIMPs and with not too many difficulties, essentially use the same framework and get a more accurate prediction of your dark matter relic density. So the final takeaway is that Friesen models are experimentally testable. I did not get to this, but we can talk about this during discussions. So thank you everyone for watching, and I look forward to interacting with all of you during the discussion sessions.